draw a free body level diagram. But I want to remind you that you did this in grade 11. And remember, they can ask you the horizontal one, they can ask you the vertical one, or they can ask you the object on the slope. One of the three you can get in the exam. But I hope you still remember how to do the one on the horizontal. That is the one they ask us to do right now. So let us do it on the board together. Right, you'll have the normal force, you'll have the weight, you have the F applied, and then you have the frictional force. Now, remember, when you draw the free body diagram, you put a dot. But when you draw a force diagram, is where you put the box. Number two, your F applied must be bigger than your frictional force. And remember, on the horizontal, it is normal force straight with the weight or the gravitational force. That is question number one we have answered, and it will carry 4 marks. But remember, every time when you draw it, you must indicate the name of the forces. Like this one is normal force, this one is the weight, and the F applied, and the frictional force. Then you get your 4 marks. The reason is the angle between the force and the x is 90 degrees. That is why there is no work. We can also prove that in the form of formula by saying W equal to F delta x cos theta. In this case, you say that F delta x cos 90 degrees. Remember, cos 90 degrees is 0. Therefore, the answer is 0 here. What I was saying, between force and the displacement, the angle is 90 degrees. That is the reason why it is done, the box does no work on the crate. First, what do we want to prove? Net work done on the box. Right. The formula is W net equal to F net delta x cos theta. Remember, on the formula sheet, the first thing on the work energy power on the formula sheet that they give you when you write exam is W equal to F delta x cos theta. Now, if you want F net, you just put net, applied, and so on. I'm not going to go in details in that one. But what is happening now is, I want F net. Then let's start with method 1. In method 1, I'm going to say F net equal to F applied plus minus frictional force. Okay. Now what happened is, the applied force is in the direction of the motion, it will be positive. The plus minus means frictional force is opposite direction. That is 30 Newton. So the frictional force is 30. Now let's substitute. F applied is 50 Newton minus frictional force is 30 Newton, which is equal to 20 Newton. So 20 Newton is the F net on the box. What is F net means? That means all the forces act on the box, or all the forces act on the object. It's only 2, applied force and frictional force, which is 20 Newton. From there, I'm going back to my F net there and substitute the 20 Newton that I've got. Then I'll say 20 times 6 cos 0 degrees. Remember, cos can be 0 degrees on the applied, on the direction of the motion. 180 degrees, it will be frictional force. But here, it was on the applied, which is W net. Therefore, we just multiply that and we get 120 joule. So that is our work done that we're proving. That we have proved our question number 3. I want to show you the second method of question 3. Right. W net equal to W applied plus W frictional force. The reason why I've got only applied and frictional force is that's the only forces that is given on our box. Right, what I'm going to do is, remember, W equal to F delta X cos theta. On the formula sheet above, work, energy, and power, the first formula given is work equal to F delta X cos theta. What you do is, if you want applied, you just put applied here, applied on the force and on the work. If you want frictional force, frictional, and then frictional here. If you want net, net, net. Therefore, here we're going to say F applied delta X cos theta plus F frictional friction delta X cos theta. That's what I'm going to do. From there I can substitute. What is my F applied? 50. What is my delta X? 6. And then cos 0 degrees. The reason why it's cos 0 degrees is because it's in the direction of the motion. So in the direction of the motion, cos 0 degrees is 1. Plus frictional force 30. And then 6. And then cos 180 degrees. Why cos 180 degrees? Because cos 180 degrees is negative 1. Then the negative 1 is going to be the force which is opposite to the motion. So the whole thing is going to give you negative. But there's something that I want to show you. On the one of method 1, there was F net, F applied, and then frictional force. Right. We had 50 minus 30, which was 20. Now, when we do this one of force, you don't put cos here on force. You put minus 30. Why? Because frictional force is opposite to the motion. And here you are taking of force. But here on work, you are taking of frictional force, delta X cos, which will be 180 degrees. What does that mean? It means you mustn't put minus 30 and also cos 180 degrees. Why? Because cos 180 degrees is giving negative 1. And then the minus 30, then it will give a positive answer. So careful, when you do force, you put minus. But when you do on the work, you put cos 180 degrees. And your force, your frictional force, is the positive value. Therefore, we have 300 minus 180 Newton, which is 120 joule. Remember, the unit of work is joule, which is J. This is method number 2. So you learners, you'll choose which one you want to do. Either first method by finding F net first, or you can go straight to the W net, which is double applied plus W frictional force. It's up to you to choose. But we both get 120 joule. That is question 3. Let's do question 4. In question 4, they say, use the work energy theorem to calculate the velocity of the box at the moment that it reaches point P. Now the question may be, which velocity are you going to calculate? Final or initial? But remember, the box was at rest. And remember, if the box was at rest, that means the VI was 0. That is the starting velocity. It was at rest, then it's 0. Therefore, we are looking for V final. Let's do the final velocity of the box using work energy theorem. Remember, this theorem, they will always ask it in metric. That's the one we did this morning. Right. I hope you still remember the formula. W net equal to delta EK. Remember, this formula is given on the formula sheet. What you do is just to copy it. And they can also ask you to state the work energy theorem. You state it from the formula sheet. The net work done on the object is equal to the change in the kinetic energy of the object. And then you get free 2 marks. You explain it from the formula sheet because it's given on the formula sheet. But let's prove it now. What is delta EK? Remember, that is half mv squared final minus half mv squared I. This formula is on the formula sheet. Yours is just to copy it. And then W net. What do we want? We want the velocity using the work energy theorem. But which velocity you want? You want the final velocity. Why? Because the box starts from rest and it moves to point P with the final velocity. Now that's the velocity that we want. So we must now substitute. What was our W net in question 3? Our W net in question 3 was, remember, 120. Therefore, we just substitute 120 half. What is the mass of the box? It's given. Remember, in physics, the mass must be in kilogram, not in gram. Then it's 35. And then V squared final. This is the velocity you want, final velocity. Minus half 30, 0. Why 0? Because it starts from rest. Remember, VI, if you start from rest, is always 0. Therefore, the whole thing is going to be 0. Then we work on this one. Now, you can take your calculator and start to calculate. But it's easy. Half of 30 will be 15. And then you take 15 to this side, you divide by 120 divided by 15, and then V squared. Remember, squared, you must find the square root from your maths. So the answer you're going to get here, you must find the square root of that velocity. And then you'll find your V final, which is in meter per second. That's the unit of velocity. So you can use your calculator and find the answer. But once you find the answer on this, you must find the square root. And then from there, you find the final velocity.